Hey, what's up, everybody? Sorry for the delay. I just want to say that presenting on Ubuntu Linux does work, except when you change your resolution and the controls go below the screen and then it freaks out. So I hope I get points for bravery for like presenting on Ubuntu. But anyway, now we're doing the iPad version, so hopefully it's better. How's everybody doing? Just eat lunch? Super high energy, right? I'm jet lagged, so I'm just gonna fake it. So my name is Pete Hunt, and today I'm going to be talking about fraud protection without labeled data. Just a little bit about who I am. Got a degree in distributed systems and started working at Facebook. Worked on a wide variety of stuff over there. Probably most well known for working on a thing called React. I'm not talking about that today. Talking about that tomorrow. But I was kind of one of the first people to be on that team and grow that and get everybody using it and wrote a lot of the code and all that. Since then, about 3 years ago, I started a company called Smite. So I was actually at Facebook, the first engineer to go from Facebook over to Instagram when we acquired them a long time ago. And the first order of business there was to plug them into Facebook's site integrity or trust and safety systems. And this is the thing that catches all the bad guys. And so we did this big effort to plug them in. And then Instagram kind of continued to just use all the other stuff that they had been using. They continued to use GitHub and Amazon Web Services and all of that stuff. But the trust and safety thing was like the one thing that Instagram really needed to leverage from Facebook's kind of tech stack, which I thought was pretty interesting. And you know, when we bought them, there were all sorts of like kind of funny policies that they had put in the code base. So if your username ended in a Z and you signed up from hotmail.com.au, like you wouldn't be able to post photos. It was just like some random policy that they had put in there. Totally weird. So I was struck by how important this problem was. Stuck around at Facebook for a while, and then started Smite 3 years ago to bring this sort of technology to everybody else. Since then, we've hired my co-founders and as well as our employees have worked on the Gmail spam engineering team, the Google Wallet fraud team, search spam at Amazon and Yahoo, Square fraud team, Stripe fraud team, those types of places. So the point I'm trying to make is that I kind of know what I'm talking about. Maybe, I don't know, that's for you to decide, I guess. So the overview for today is I'm going to talk about what is trust and safety. You came to talk about fraud, and I put trust and safety up there, and I'm going to explain why in a second. We're going to talk about automated classification. So this is a software conference. We should be trying to automate as much as we possibly can. I'm going to talk about the software systems that we put in place to do that, as well as a deep dive on the infrastructure to deliver those systems. Does this sound good? Is this what you came for? Okay, that's good. That's great. I wonder what that guy's talking about. All right. So, what is trust and safety? When we're talking about trust and safety, we should first really talk about fraud. So when we talk about fraud, the canonical example that we think about is payment fraud. Specifically, like stolen credit cards are a really popular example. So somebody manages to get their hands on your credit card, they go buy something on some service, they get the item, and then you see a fraudulent charge on your bill. Then you call up your bank, you say, what the hell, I didn't buy this thing. The bank then takes the money back from the merchant, and the merchant is stuck because they shipped the product to the fraudster, and they also didn't get paid for it. There are other types of fraud that we talk about too. Fake accounts is another one. So creating a bunch of fake accounts to do something, we would consider those kind of fraudulent accounts, and those can be used in a number of different contexts in a number of different ways. And compromised accounts, also known as ATOs or account takeover, is the third type of fraud that you hear a lot about. So somebody gets into your account somehow, like they hack your account, and they either drain some stored value, or they steal your information, or they just kind of do something sketchy with it. So those three things are what we hear about a lot, but when you start to zoom out and think about what those compromised accounts or fake accounts can actually do, it starts to get a lot broader. So spam and phishing are two really popular things. So you see spam everywhere, and people are trying to phish you all the time. This is something that if you want to do it at scale, you have to compromise someone's account or create a bunch of fake accounts. Targeted harassment as well. You might not think of that as fraud, But if harassment becomes a big problem, a lot of times the strategies that the harasser employs fall under the category of fraud, and they're violating your terms of service, which you could consider fraud as well. If you've got a marketplace, there's not just buyer side fraud and stolen credit cards. There's malicious items malicious sellers. So if you've ever tried to rent an apartment on Craigslist or whatever the Swedish equivalent of Craigslist is, if it's anywhere like the San Francisco Bay Area, there's a lot of fake listings out there that the price is too good to be true, or maybe you see an iPhone for sale and it's super cheap and you're really excited about buying it, and then you reach out to the seller, they say, hey, like wire me the money and then I'll mail you the iPhone. If that happens on your service, your users are going to get pissed because they're getting ripped off. There's also buyer-seller collusion as well. So maybe I've got a crowdfunding site and I've got a bunch of stolen credit cards and I want to figure out a way to turn those stolen credit cards into money. So I create a crowdfunding campaign for myself, I start to fund it myself, and then I cash out and I've got a bunch of money. So there's all sorts of different types of fraud out there, and it's not just as simple as stolen credit cards. And so you can actually use the same set of fundamental tools, both software tools as well as operations and policies, to solve all these different problems. And so that's why rather than talking about fraud, I'd rather kind of give it a name that encompasses all those different use cases. And the name that a lot of big companies use these days is trust and safety. So from here on out, I'm going to be talking about trust and safety. That includes the kind of fraud use cases that you know and love, as well as some of the new and more interesting ones. This making sense so far? You guys on board? Cool. So we can walk through a couple of like very specific examples. I already kind of talked a little bit about credit card fraud, but if you're a really good credit card fraudster, like here's how it works. Somebody gets into a taxi cab and they take a ride, and then the taxi driver says, oh man, my machine's broken, like I'm just gonna write down your number and then charge you later. They do that a bunch of different times, and then they go and they sell those numbers online in a marketplace. And then somebody who actually wants to do the fraud goes and buys those numbers from the marketplace. They test them to make sure that they still work by basically running a lot of $1 transactions to see if they clear, or cheap transactions to see if they clear. And then they immediately commit as much fraud as they possibly can in the shortest amount of time possible in order to maximize the amount of money they can get while those cards still work before the person's figured out that their card was stolen. And so a great way to do that is you have a grocery delivery service or some other real-time delivery service, and you buy a bunch of stuff with it because it's going to get delivered within an hour. So unless they figure out that it's fraudulent within an hour, you're going to get your items. And then you can have them delivered to a street corner so they don't even know the address that you were getting them delivered to. Another way to commit fraud is you can steal someone's account. Everybody's heard of the LinkedIn password breach, or that Yahoo had 3 billion accounts breached, and MySpace and all these companies. And the thing is, a lot of people reuse passwords. And so if you're able to get your hands on one of these databases, you can go and try that username password combo on a bunch of different services, and a lot of times it'll actually work, and then you can do some damage. And finally, and this is kind of the most, I think, dramatic and personal one, is romance scams. So if you think of fraud or these types of attacks as a sales funnel, it's just like any other sort of sales and marketing funnel. So you have a big list of qualified prospects at the top that you think are good candidates for defrauding people, and then you basically start to narrow them down. You qualify the leads. You're like, all right, who's the most vulnerable person that I can get? You qualify them down to the set that you think are most likely to convert, and then you go and give them targeted messaging in order to convert them. So a great example is if you can find some lonely elderly singles online, and there's a lot of them. A lot of times they're the most likely to fall for one of these scams. So you start an online relationship with this person, you get them feeling really comfortable, and then you say, hey, I'm stuck in the airport, can you wire me some money to get home? Of course they'll do it. And then because you're their online boyfriend or girlfriend, and then you disappear. And it's people get scammed like this all the time. It's a huge bummer. So if you don't have anything in place to stop this sort of thing, here's what happens. So the bad thing happens, and then a user will write into your customer success team and they'll complain, or you'll get a chargeback. And when either of those two things happen, you probably have to issue a refund, which means you lose some money. or the user churns, which means your brand gets damaged and you might lose some money, or worse, maybe they'll come at you and sue you, or maybe the government will go in and come and try to regulate you. So everybody's interests are aligned here. Like we want to protect the user so they don't get hurt, but you also want to protect your brand and your bottom line. So kind of the most basic way to solve these problems is to implement some sort of manual review process. So anytime somebody wants to get paid out on a crowdfunding service, or maybe anytime they list an item for sale on a marketplace, it goes to a manual review team. They take a look at who's putting it up, their history, and they decide whether or not we want to allow this marketplace listing or this transaction or this registration or whatever. There's a lot of problems with this. First of all, it's really expensive. You have to employ a lot of people in order to do this, and if you're going to manually review every single thing, it doesn't scale very well. The second problem is that it's slow. So I'm the most risky user I can be right when I sign up because I'm a brand new account. I'm also the most engaged I'm ever going to be with the product in the first 5 minutes that I use it. So I want to get value out of the product as soon as possible. If I have to be stuck in some waiting period for a couple days before I'm approved to do the thing I want to do, that's going to be a pretty big bummer too. And finally, depending on the use case, this job can be really unpleasant. If we're reviewing images being posted or comments being posted, a lot of times it actually has real psychological impact on the reviewers. So we want to minimize the amount of manual review as much as possible. And the way that we do that is we only review the risky transactions. So we have some piece of software that goes in, and there's a transaction, and a transaction can be any one of those things. So it could be a message being posted, a registration, a credit card payment, a marketplace item being listed, whatever. And at a very, very high level, we want to bucket it into one of 3 buckets. It's either low risk, so the majority of transactions should be low risk, and we just want to let it through, just like normal. There's a set of high risk transactions, which are like stuff we know is bad and we know we just don't want to allow. So maybe we have a known blacklist of email addresses. We just don't want to allow anything from there. And then there's this kind of medium risk bucket that needs some manual review. And again, this depends on your particular application and use case, whether or not you have a big manual review team or a manual review team of just like one person spot checking stuff. But the real trick is, how do we determine what constitutes low versus medium versus high risk? So in order to make that determination, you got to think about the business objectives. So we've got kind of 3 goals that all have kind of conflicting, or that all kind of press on each other a little bit. The first thing is we want to protect the brand and the bottom line. So we want to protect the end user because we don't want reporters writing about how terrible we are, and we don't want to lose a bunch of money to chargebacks. We also want to improve growth. So actually, if you look at the numbers, businesses in the United States lose 10 times as much money to false positives from their fraud system. So that means we block a legitimate transaction versus actual fraud itself. So we want to make sure that we can continue to grow our user base by not blocking legitimate users that are trying to do the right thing. Or maybe somebody's just traveling. We don't want to just block anyone just because they're in a country they've never been in before. And finally, we want to reduce costs. We don't want to manually review. We want to manually review as little as possible, preferably nothing. So we have to increase the confidence of our classification. So that's kind of the quick overview of trust and safety. Let's talk about how the automatic classification actually works. There's a number of different ways that you can go about this. We need a little bit of a framework to think about this. I probably put too many words on this slide, so just read the first line of the bullets. So the first metric you might think about when you have an automatic classifier. So an automatic classifier says, given this transaction or this thing, basically I want to pick one or more categories or buckets that it falls into. So you could think of this as, for this example, it classifies a transaction as good or bad. In reality, you would want to classify it in a little more nuanced way, but for this example, let's say it's good or bad. So the first metric you might want to think about looking at is accuracy. So what percentage of transactions did we correctly predict based on some feedback signal that we have? So if we have a data set where we have a source of truth, like, hey, these are the known fraudulent transactions, these are the known good transactions, what percentage of those did our classifier automatically predict correctly? This metric actually really sucks in the real world most of the time, because a lot of times you don't have very balanced classes, so only 1% of your transactions are going to be fraudulent and the rest of them are going to be good. So we could write a really simple classifier that just says, yeah, everything's good. we can automatically get 99% accuracy because we just completely ignore all the bad stuff. So it's a little bit better to look at two other metrics. Precision. So what precision is for everything that we classified as bad, what percentage of those things were actually bad? So it's kind of a measure of false positives. So if we have a high precision score, so if 99% of the things that we classified as bad were actually bad, that means we have a very low false positive rate. There's another metric called recall, which says for everything that was actually bad, what percentage of those did we flag as bad? So this is the other side of the coin. So what high recall means is if we have high recall, we have low false negative. So we caught more of the fraud. Now there's some tension there because the more fraud that we label as fraudulent, the more likely it is we're going to have a false positive. So there's this line that we have to ride between like, hey, what's the trade-off for a false positive versus a false negative? And that's how we kind of set that boundary. So if we wanted to implement this in an automated way, the first thing we would do is we would probably write a rule. And this is actually probably how most of the credit card fraud, at least in the United States, is caught today, is through a big old list of rules. And so this is an example rule in some pseudo language. But basically, what this is saying is that we're keeping track of all the transactions coming from an IP address. And if you use more than 10 unique credit card numbers in the last day, we want to refund all the transactions coming from that IP address. So again, this is like, I've bought this giant list of credit cards on the internet somewhere, and I'm just running $1 transactions on all of them to figure out which ones are good and which ones are bad. This rule is gonna fire if I'm not smart about the number of IPs that I shard over. So there's a lot of advantages to writing a boring rule like this. It's really easy to explain. I can explain it in plain English. If I'm a third-party vendor and I'm going to a customer and I'm saying, hey, like, don't take this person's money, I can point to this rule and explain exactly why they shouldn't take that person's money. It's really easy to tune too. If something breaks, we can go in, we can change the rule, and then we can move on with our lives. And almost most importantly, there's no labeled data involved. So we don't have a training set here. We just use a little bit of human intuition. So we say, yeah, if somebody uses more than 10 credit cards from the same IP address, that's probably a bad thing. And because we know a little bit about the psychology of the attacker and what they're trying to do. So we don't need any labeled data. The cons here are we pulled that threshold of 10 like kind of out of nowhere. You might have a data scientist or an analyst that goes through and does a SQL query to try to determine it, but you pick it out at some point, you put it in the rule, and then it just sits there until you decide to update it. And attacker behavior can change over time. Maybe they figure out, hey, the threshold is 10, so I'm only going to run 5, and then I'm going to buy some more IP addresses and keep doing my fraud campaign. So there's a lot of problems with rules. So the next thing to do is to try to take a machine learning based approach. And so if you said the words machine learning between 2008 and 2015, you instantly got $2 million of Silicon Valley funding. From 2015 on, you replaced it with either deep learning or AI, and then you got $4 million of funding. So we got this machine learning hammer. Let's go find some nails. That's how I look at a lot of these AI companies. Oh man, we got all this money. Like, what should we spend it on? So a quick note on machine learning. Everyone's talking about deep neural networks today, and they're doing some really, really cool things in self-driving cars and image classification, stuff like that. But 9 out of 10 people you're going to talk to in the industry that are using machine learning to solve a problem are using like a pretty vanilla linear classifier or random forest model, which is kind of like machine learning 101 type of stuff. So the models themselves are not super clever, and you can probably spend a couple hours on the scikit-learn tutorials page and learn 80% of what you need to know to understand it. So if we wanted to take a machine learning based approach, we have to get a labeled data set, and we give it some features. So maybe we give it the IP address or the credit card or some other features that we would engineer. And then we give it, an example of a transaction that was good, a transaction that was bad. It does its magic machine learning stuff. I'm not going to really talk about how that works. And it will kind of give you a confidence score as to how likely it is that this thing is fraudulent or not. And so we can, basically say, hey, if the model has a 90% likelihood that this thing is fraud, we're going to refund the transaction. So there's a lot of advantages to using machine learning for this. It automatically determines the correct thresholds and parameters. So nowhere did we magically say, hey, if you have more than 10 payments from a given IP with unique credit cards, do we block this transaction? It's possible that the machine learning model inferred that rule or something somewhat similar to that rule, but it used statistics to figure out like what that threshold should be. It also adapts to changes in attacker behavior. So if we retrain this model, every night or every hour, or we use an online learning method, as user behavior changes and attacker behavior changes, this model is going to adapt accordingly. There's a lot of cons with this. It's certainly harder to explain how this model works to somebody versus a rule. Now there are ways to explain some linear models, but it's harder to explain. And it's very difficult, if not impossible, to tune these without implementing some sort of rules engine. And finally, the worst part about using machine learning model is the reliance on labeled data. And labeled data in the real world really, really sucks. And also the features that go into the model are a lot of the magic of machine learning comes from the features that you put into it. So why does labeled data normally suck? It's noisy, so maybe you don't have perfectly accurate labels. Maybe you're missing some fraudulent transactions. Maybe you've got human reviewers doing these reviews, and each reviewer is inconsistent with each other, and so it's hard to have an accurate representation of what's going on in the data set. It's expensive sometimes, so again, if you're going to employ a bunch of human reviewers to create these labels, that costs money. Two total non-starters for the data, though, are that it's often delayed. So we get a chargeback maybe 60 days after the transaction happens. And so it's going to take us 60 days to adapt to new types of attacks. Other applications might adapt quicker. So maybe you've got bystander reporting on your social network and people are reporting this stuff a couple minutes after it happens. But then you also have a noisy data problem. People will report things that they disagree with, not necessarily like spam. And finally, for some applications, you just can't get the labels. It really depends on your application. And the other thing is that the machine learning model is only as good as the features you've engineered, and this is an adversarial problem. So you have an attacker on the other side who is trying to defeat your system, and what they're doing is they're trying to figure out what features are you looking at, and can I blend in with the crowd for those features that we've selected out. So a lot of times, if your adversary is any good, the pattern is going to be you deploy a model, it works for a couple of days, the adversary figures out that you're looking at some feature, they rotate that feature, then your model is essentially blind to that attack. You've got to write a new feature, deploy that, retrain a model, get new labeled data, that type of thing. So we found that most companies don't actually have a lot of success with supervised machine learning in a general sense. For specific applications, it can work well, but it has a lot of problems. And so the solution is, of course, deep learning. No, I'm just kidding. The solution is to take some simple rules that you can explain and use some really complex, interesting features that do adapt over time. You can think of this as unsupervised machine learning or anomaly detection. But I'll give you an example of what I mean. So this top rule right here is the one that we had before for credit card testing. So if somebody's used too many credit cards in the last day, we want to refund their transactions. And we don't want to ship the item, by the way. We can switch that hard-coded threshold to a dynamically adapting one by simply plotting a histogram of the whole population and seeing okay, for every IP in our service, what is the median number of credit cards they're using, and how many standard deviations above the mean am I? Or what percentile am I? So if I'm in the top 1% of all IP addresses by the number of credit cards I've used, that is interesting. Now this rule actually will have a lot of false positives, but we could combine this with a couple other very basic predicates to get a really powerful rule that will adapt over time. And if during the Christmas season people are making a lot more purchases on shared IP addresses, this will automatically adjust that top 1% threshold based on what the whole population is doing. And so there's a lot of different ways you can apply this type of technology. I've been talking a lot about kind of credit card testing, but there are other ways to do it. The advantage here, the first three advantages are exactly the same as rules. So I can explain that rule, I can tune that rule. If the top 1% isn't enough, maybe it's the top 0.1%. I can tune that if we see too many false positives or false negatives. We don't need any labeled data. We're automatically adapting just based on the real-time data stream coming in. And it's adapting to changes in behavior. We can also do this for spam detection. So let's say people are uploading the same images of Ray-Bans over and over. Like if you've been on any popular social network that I may or may not have been previously employed at, you'll see this Ray-Ban spam where they're like, hey, like get these cheap Ray-Bans for $9.99, click here. So we can write a simple rule that uses streaming statistics to solve this as well. So let's download the profile picture they're using or the image that they posted. We'll do a SHA-1 hash or a better hash, which I can talk about in a second. There's a typo in my slide, sorry. We'll count the number of times that people have uploaded this image today versus yesterday. And if it appears 10 times as often today than it did yesterday, and it appeared more than 5 times today, then we're going to want to block that upload. So what this is detecting is like basically, hey, we're seeing a huge spike in this image. And that generally indicates that they started out testing whether this image was going to work or not with a couple accounts, and then they really started blasting it out to everybody. And so again, we have no sort of feedback from bystanders. We have no labeled data. This is all real time. And we're just kind of able to think a little bit about what the attacker's trying to do and encode that in some very simple tunable rules. Is this making sense so far? All right, cool. So all that stuff sounds really good. And by the way, like Facebook and Google have teams of people writing those rules and tuning those. And you need some infrastructure to run this stuff. And so I'm going to give you kind of the simplified infrastructure, and we can talk about kind of how it gets more advanced over time. But basically, there's a really easy way to do this, which is you can run a nightly job on BigQuery or Amazon Redshift or whatever your data warehouse is. Basically, take those rules, turn them into a SQL query, and then pull the list of transactions that you think are fraudulent or accounts that you think are fake, and then do something every night with those or every hour with those. What really sucks about that is you want real-time classification. So like when if you're running an on-demand service, when the transaction happens, you want to know whether it's fraudulent within like 30 seconds so that you can like throw the pizza into the oven and then go like deliver it as quickly as you can. And you also want to do real-time online learning. So if you're at any sort of scale and your attacker is again, adapting to your signals, you want to be able to adapt those signals online at low latency. So the way that you generally build a system like this is we get an event. So the event is like user wants to make a payment, user wants to post a thing, user wants to list an item. Then we have our rules. The rules go pull some of those features from the database. So they do they pull some of those streaming statistics from the database. They update those statistics as needed. So they increment the count or they add the credit card to the set of current credit cards seen for this IP. They make a decision and then they write those values back to the database so the next transaction that comes in can take advantage of the learnings from the previous one. So this infrastructure looks a little bit like this. We've got our web app over here. It's a Rails app, Django app, whatever. It sends the event to some rules engine that makes the decision. There's a data store that stores the state, which is mostly just kind of streaming statistics. And then it sends the classification result back to the app. So there's a lot of problems with that, or a lot of challenges to solve. So a lot of times we're fetching maybe tens, if not hundreds, of different statistics for a given transaction. Storing that data can get expensive because it's big. We want to do this at low latency so we don't slow down the user experience. And we also have to deal with availability, so we don't want the system to go down. And we want to be able to scale it out. So we want to fetch multiple features. Like think about this, right? So we have to wait for the URL to download. Then we have to do 2 round trips to that data store to get those counts. The way that Facebook and Google and Smite and all these companies do it is they make this language a domain-specific language. Facebook's open source version is called hacksoul. If you think your analysts can write Haskell, then they can use that. I don't think that a lot of data analysts want to write Haskell, but you can check that out. But basically, conceptually, if you're writing JavaScript, you want to kind of translate it to something like this. So hey, we download we download the URL, then in parallel we do these two counts from the back end. And so this is kind of a classic asynchronous I/O type of thing. If you've ever written like G-event in Python or done any sort of I/O in Node.js, it's very similar. The difference is because this rules language is pretty simplified and pretty restricted, you can oftentimes add this parallelism automatically rather than require the programmer to actually write those await statements in there. So the second problem is storage size. So a lot of the stuff that we talked about was like doing set cardinalities. So I want to do a count unique. So how many unique credit cards has this IP used in the last day? So I need to store every single pair of IP and credit card and then do an aggregation. And when you're at scale, that can get kind of expensive. And if you're doing something besides transactions, maybe you're looking at user logins or users sending messages, and we're keeping track of sets for each unique user, that can get really too expensive. And so what we can do is we actually don't need exact results for this. We can use something called a sketching or an approximate data structure to basically get an estimate for, hey, how many unique IP or how many unique credit cards did this IP use in the last day? We don't actually care what those credit cards were. We just want to know the count. And so there are a couple clever data structures, like a sliding window hyperlog log is one, a countmin sketch is another one, and they can save like 90% on your storage. I made that number up, but like it's a lot. And you also want to use a data store that has compression. So if you're using MySQL, for example, there's a storage engine from Facebook called MyRocks, which builds it on top of RocksDB. And so you get some compression for free with that. Round trip latency was the other big performance concern that we've got. So if you think about kind of what we need to do whenever we receive an event, so we receive this transaction, we have to kind of do these statistical counts and then update the counts and save them back to the database. A lot of these data structures can actually be pretty big. So countmin sketch saves you a lot of space, but you have to download the whole thing, which might be 200 kilobytes, update it, and then write it back. And if you're going over the network, that can be kind of prohibitively expensive, or you're wasting a lot of bandwidth. So instead, the way that a lot of the big companies do it and the way that we do it at Smite is you can build an extension into your database. So if your data store is Redis, you can write a Redis module or a Lua script. If you're using something like MySQL, you can compile an extension in. What we do is we actually have our own databases built on top of an embedded storage engine that understand the sliding window hyperlog log algorithm and the countmin sketch algorithm. And so rather than downloading this opaque chunk of bytes, parsing it, updating it, and writing it back to the database, you just go to the database, you say, hey, database, like, what's the count? And it sends you back the value, which is like 8 bytes. And then you just send it a message that says, hey, add this thing to the set or increment this thing, which is basically no overhead. Another performance issue that you got to think about is disk latency. So most companies that are at scale try to find a way to hold most of the data in memory. There's obviously going to be a long tail of data that you want to flush out to disk, but most transactions that come in should really only hit memory. So if you're building a traditional web app or CRUD application, you would immediately reach for memcache, and you would say, okay, I've got this slower database, I want to put memcache in front of it to make things faster. The thing is that every transaction that comes in reads some data and then immediately invalidates it because it updates these counters. So actually the traditional way that you would use memcache as a read-through cache doesn't really work very well for this application. Instead, you really want to talk to the database directly and find a way to really optimize what sits in memory versus what sits on disk on the database itself. If you're at a smaller scale, you can use something like Redis that just keeps everything in memory, and you can just throw memory at the problem, or throw money at the problem until it becomes a big issue. That's what we did for a long time. Another thing on that list that I mentioned was high availability is something that we got to worry about. So if you remember that diagram where we had these events coming in and classification results coming out and updates going to the database, we use something called Apache Kafka, and we basically just put Kafka in front of every single one of these services. And what this means is that any of these systems can fail independently, and we won't lose any data. And also back pressure is really important. So if it's Black Friday and we see this big surge of transactions coming in, and the data store can't process the writes fast enough, we want the data store to be able to say, hey, like, I'm just going to serve stale data for a little while. So even though the fraud system might not be operating as effectively as it would be if it wasn't behind, it's still up and still able to help somewhat. And so by introducing Kafka there, we're able to kind of have some back pressure and not overwhelm the database, so we can still serve reads out. And then we can even, if the rules engine is the piece that fails and gets too slow, we can have some back pressure there as well. So that's kind of how we get high availability. It also lets us create, Jesus, lets us create multiple replicas. So we can just spin up a second copy of the rules engine, second copy of the data store, and Kafka can manage all those replicas for us. Similarly, because we're leveraging Kafka, we can start to scale out horizontally. So if we've got so much volume that one data store can't handle it, or one instance of the rules engine can't handle it, one data store can't handle it, we can start to do kind of traditional sharding. So generally what that means is whenever we're computing one of these statistics, we pick the shard based on that first parameter. So maybe we have 20 different data stores. All the data associated with that one IP address goes onto one of those instances. And then we can create multiple replicas of those instances. And it's a pretty boring sharding story at that point. So we call this the Smite DB architecture. We're not really doing a lot of the thought leadery marketing crap. So like we have an example of our rate limiter up there if you want to kind of see the code that implements some of this stuff. Not a lot of people use it except for us, but a lot of this stuff is in production and it works pretty well. So we're getting to the end here. What didn't we cover? So there's a lot of advanced features that we could look at that I haven't really talked about. There's a whole family of perceptual hashes that you can use to stop various types of spam and fraud. You can actually use some of this cutting edge deep neural network stuff to create something called an embedding, which is, for the purposes of this talk, kind of a next generation perceptual hash. Happy to talk about that afterwards if you'd like. You can leverage IP metadata. So we get an IP address. Maybe we want to cluster not only by the IP address, but the subnet and also the ISP. And finally, there's a whole class of interesting things you can do with nearest neighbor search. From the database side, we didn't talk about durability, and we didn't talk about bounding the memory footprint. There's a bunch of different things that you can do there. And finally, the tooling here is kind of one of the biggest challenges. So experimental rollouts are really important. This is one of these things where with great power comes great responsibility. You deploy a rule that blocks 100% of payments, you're probably going to get fired, or your company's going to go out of business. So you really want that. You really want the ability to do kind of unit testing of your rules and the underlying data stores. And monitoring is actually like the biggest challenge, because sometimes it's hard to tell whether your infrastructure is fucking up or whether you're just getting attacked. So if our block rate goes up to 90%, like, are we blocking a bunch of legitimate users, or are we just getting a ton of spam or a ton of fraud or a ton of bad stuff coming in? So monitoring, I think, is actually like the most challenging thing of all these. Just for a little recap, I think companies are starting to look at this as a holistic trust and safety problem, not just as an isolated fraud problem. Rather than looking at all these problems in isolation, if you look at them with one unified system, you're going to do a much better job. What we found based on our work at companies like Facebook and Google and all those places is that rules that leverage streaming statistics are often the right trade-off of explainability and tunability versus adapting to new behaviors. Again, there's not one solution to everything. It's a whole spectrum of tools. You can use some off-the-shelf infrastructure like Redis, like Kafka, until you hit scale. At some point, you're going to look at your Redis bill and you're going to be like, oh my God, I'm paying like $30,000 a month for Redis, and we got to go fix that. And finally, this is an adversarial environment, so your work is never done. Our goal at Smite and a lot of these anti-abuse teams within companies is like, make it too expensive to abuse our customers so that they go to the competitors. And then we go to the competitors and we sell our product and then they go. But seriously, like that's like we're not going to the country of origin of the attack, knocking on their door and like taking them to jail. Like we're just trying to make it expensive enough so that you don't abuse our service and that the attacker goes and goes somewhere else. So with that, that's my whole talk. Thank you guys for.